So the first law of thermodynamics is often summarized as there is no free lunch. So thermodynamics is where we're studying energy and how it converts between different forms. So the first law of thermodynamics really is the law of conservation of energy. The total amount of energy in the universe is constant. You cannot produce a system that will create energy. People used to try to patent these perpetual motion machines that seem to, keep moving without any input of energy. Well, they were all fake. There was some hidden source of energy. You can't have something that produces energy without using energy. So you cannot get something for nothing. There is no such thing as free lunch, right? They offer free lunch in the public schools. Well, is it free? No, the taxpayers are paying for it. It doesn't cost the children anything, and it's a really great thing, but it's not really free. So there's no free lunch. We need to talk about state functions. So now we're going to talk about mountain climbing, or just regular hiking. So here we have a picture of a mountain, and there's path A that is 12 miles long, and it snakes back and forth and back and forth, and this is a typical kind of trail. And then there's path B, which is only 5 miles long, but it is straight up the side, right? My son Tommy would take that path. When you go from the bottom to the top, your change in elevation is 10,000 feet, because you've gone from sea level to 10,000 feet above sea level. Your change in elevation is the same whether you took path B or path A. The change in elevation is exactly the same. Is the distance you walked the same? No. If you went this way, you went more than twice as far walking as you did going straight up the side. But the change in elevation is the same. I choose path C, which is to get in a helicopter and go and just be set down on top of the mountain, right? But again, 10,000 feet is the elevation change. So a state function does not depend on how you got there. It just depends on where you started and where you end up. Distance traveled is not a state function. So internal energy is all the kinetic and potential energy of everything that's in the system. And again, the system is however we define the system. Internal energy is a state function. Its value only depends on the state that the system is in and not how the system got there. So because it's a state function, we can say that the change in internal energy, delta, so this is the Greek letter delta, it's a triangle, and that generally stands for change in. So the change in E, the internal energy, is going to be equal to the final energy minus the initial energy. Just like the change in elevation would be your final elevation, 10,000 feet, minus your initial elevation, which would be 0. In chemical systems, we can think of the reactants and the products as the initial and final states. So if we're talking about this reaction, the initial state is the reactants, and the final state is the product. So in this reaction, the reactants, carbon and oxygen, have higher internal energy than the product, CO2, does. So when this reaction happens, then the change in internal energy for this system is negative. Where did the energy go? It went to the surroundings. So if the system is losing energy, its change is negative, then the surroundings are gaining energy and their change is positive. We call this an energy diagram, And you can think of it a lot like the picture of the mountain, where, you know, you're starting here and ending there, or in the next slide, we'll start down here and end up there. And what we're looking at is the change in energy, and it doesn't matter how you went in between, it's just the initial and final. So in this example, we've turned, no, I'm sorry, jumping ahead, this one is still the same. So here, our reactants have more energy than the products, so the energy is lost by the system. Delta E for the system is negative. The energy lost by the system is gained by the surroundings. So delta E for the surroundings is positive. So if I give you a $10 bill, that's positive 10 for you and negative 10 for me, right? If you give it back, that's negative 10 for you and positive for me. It's still 10, right? It's $10, and whether that's negative or positive depends on what side you're looking at. What are you defining as the system, and what are you defining as the surroundings? So it's a lot like transferring money between accounts. Here, we're looking at the reaction in reverse. Carbon dioxide decomposing to form carbon and oxygen. Well, if the forward reaction had a negative change, then the reverse reaction has to have a positive change. And it has to be the same amount. So here, our reactant, the CO2, is lower in energy than the products. So this is the previous one. CO2 is lower energy than carbon and oxygen. And a lot of that's based on their chemical potential energy. And so when we change it here, we still have carbon and oxygen at this higher energy state and carbon dioxide at the lower energy state. But now we're going from here to there. We're going up. And so this system is gaining energy. If the system gains energy, energy has to come from somewhere. You can't just make it. So it's coming from the surroundings. So we can say, yes, this is, we are working up to endothermic and exothermic. Yep, exactly. So the energy for the surroundings is the same value. The energy change is the same value as the energy change for the system. It's just that the sign is opposite. So if I give Tracy $10, it's negative for me and positive for her, right? So we can say that the change in money for Jody is equal to negative change in money for Tracy. If my delta money, my change in money, is positive $10, then that means that Tracy is negative $10. If mine is negative $10, hers is minus $10 or plus $10. Okay? This thing where we have two things that are equal but opposite in sign just messes with students. And they think that that means that this one's negative. No, it doesn't. It means that this one is opposite in sign to that one. So, we could say, if I'm changing $10, gaining $10, then Tracy would be losing $10. But if I'm losing $10, then Tracy's gaining $10. Okay? It's just the direction. Whether you view it as positive or negative depends on which end you're looking at, right? It's point of view. So when the reactants have higher internal energy than the products, the system is losing energy. Energy flows out and into the surroundings. If the reactants are lower in energy than the products, it's gaining energy. And so again, energy is like money. The system is like your bank account. Money leaving your account is a withdrawal, and that's a negative, right? You can look at your online statement and it says negative. This money left your account. If you have money entering your account, that's called a deposit, and that's a positive, right? So we can think of energy as being very much like money. It really helps with the signs. Okay, consider these fictitious internal energy gauges that describe the initial conditions for a chemical system and its surroundings. So here's the system, 3/4 full. Here's the surroundings, 1/4 full. Which of the energy gauges corresponds to final conditions following an energy exchange in which the system, delta E for the system, is negative? So if delta E for the system is negative, has the system gained energy or lost energy? It has lost energy. So we see here that the system started out 3/4 full. So if it loses money, then its tank must go down, right? Well, this one went down, and this one went down, and that one went up, right? So it can't be C. So now we have to choose between these two. What's wrong with B? The system went from here to here, and the surroundings didn't change. The surroundings need to go up because that energy has to go somewhere. And the way we've defined system and surroundings, system is the thing we're looking at, the surroundings is the rest of the universe, right? So there's nowhere else for the energy to go. It goes into the surroundings. So this doesn't work because this would represent a loss of energy, and that's not possible. So it's got to be A. Does that make sense? So heat and work are ways to exchange energy between the system and the surroundings. They are not state functions. They do depend on how the process happens. So we can say that the change in internal energy is equal to the heat plus the work. So we have to have sign conventions for heat and work because these can go directions as well. So Q represents heat. Don't ask me why it's Q. I don't know. So we say that the Q is positive if the system is gaining thermal energy. Right? This lines up with our ideas of money, where it's a positive if money comes into my account. Q is negative if the system loses thermal energy. Okay? What about work? Well, it's positive if work is done on the system. It's negative if work is done by the system. That one's a little harder to understand. So let's think of giving a friend a nice shoulder massage, right? That's doing work on your friend, right? You're exerting effort and massaging your friend's shoulders. And some people get paid for that. It is literally their work, right? So if I'm doing work on my friend, that's kind of negative for me because I'm expending energy. But it's really positive for my friend. Like, oh, that feels so good. Do it some more, right? So, is the system doing the work? That's negative for the system. Is work being done on or for the system? That's positive for the system. And if we're looking at the change in internal energy, again, positive if energy is flowing in, negative if energy is flowing out. Any questions? So let's look at some transfers of energy, again with the pool table. So here we have the white cue ball. It has an initial kinetic energy of 5 joules based on its motion, its mass and its velocity squared times 1/2. So it's rolling across the table. Because this is a real pool table and not a fictitious table, there is some friction on the table, right? If you roll a ball across your carpeted living room, is it going to make it to the other side? Probably not, unless you really rolled it hard. But if you rolled it on a hard surface floor, like if we rolled a ball on this floor, it would go a lot farther, even with the same push. Why? Well, the carpet has a lot more friction, right? So as this ball rolls, we're losing energy due to that friction, and that is energy lost to heat. It's a transfer by heat. So if you rub your hands together, what happens? They get warm, right? Why is that? Friction. Friction. If you've ever used an electric drill, you drill a hole and touch that bit after it comes out, oh, hot, because it was spinning really fast against the wood, lots and lots of friction, and so there's a lot of heat there. So as this ball rolls across the table, it's losing heat. So it's going to lose 1/2 joule of heat. So when it gets over here, it has 4.5 joules of energy left. So here, Q for this ball is negative. We've lost 0.5, right? And then when it hits the other ball, it's doing work on the ball. After collision, its kinetic energy is 0. It has transferred the remaining of its kinetic energy to the purple ball. So we have the work for the cue ball is minus 4.5 joules, and the heat lost by the cue ball is 0.5 joules. And so together, these add up to a -5 energy change. Delta means the final energy minus the initial energy. Its final energy is 0. 0 minus the initial energy is -5. So if the system, that first ball, lost 5 joules of energy, then the surroundings had to gain 5 joules of energy, right? And here the system is the ball, the white ball. The surroundings include the table and the purple ball and actually the rest of the universe. Does that make sense? So the energy is being transferred through the method of heat and work. Okay? So that's a good, well-maintained pool table. Well, what if we have a rough pool table? So this is more like rolling the ball on your carpeted living room floor. We're going to start out with the cue ball with the same amount of kinetic energy, but now as it rolls across, there's a lot more friction, and so it's going to lose 3 joules of energy to heat. The heat will go into the table. So when it gets over here, then it only has 2 joules left. So it transfers those 2 joules to the purple ball, and now it has 0. The change in energy, delta E, is the same as the previous table, right? The final condition is 0. The initial condition is 5. 0 minus 5 is -5 joules. It's the same because energy is a state function. But the work and the heat are not the same. Here, the work was -2, and the heat was -3. They add up to the same, but they did not go in the same way. Does that make sense? So heat and work are not state functions. It depends on the process. It depends on whether this is a rough table or a smooth table. But the overall change in energy for that white ball does not depend on whether it was a smooth or rough table. Any questions? So delta E for the white ball is the same in both. Q and W are not. The sum of Q and W is the same for both, even though the individual values of Q and W are different. Okay. This looks like a nasty problem. There's lots and lots of words, but it's actually pretty simple. A cylinder and piston assembly, defined as the system. I'm not sure what I said there. A cylinder and piston assembly, defined as the system, is warmed by an external flame. The contents of the cylinder expand, doing work on the surroundings by pushing the piston outward towards the external pressure. If the system absorbs 559 joules of heat and does 488 joules of work during the expansion, what's the value of delta E? This is not a dimensional analysis problem, but we can still highlight our numbers and highlight the question. So we're asked what delta E is. That's not what I wanted to do. Well, there was an equation for that we just heard about. Delta E equals Q plus W. Heat can transfer energy either way. Work can be a transfer of energy either way. The sum of those will give us the change in energy. So here we have the word work, right? So 488 joules of work. Well, that tells me that W is 488 joules. The question is that positive or negative? So the system is the cylinder and piston, and it says that the system does work. If I do work, is that negative or positive? Negative. Me giving someone else a massage, right? I'm having whatever. Anyway. And then here it talks about the system absorbing 559 joules of heat. Well, Q is heat. So Q is 559 joules. And if the system is absorbing heat, is that positive for the system or negative? It's positive, like $559 coming into your bank account. I think everybody'd appreciate that, right? So this is positive. So that's how we identify the sign of these things. So then we can use these in our equation. Q is 559 joules. I'm going to put parentheses around them so we can see that they're matching up with this equation, plus the work, which is negative 488. So 111. So delta E is 111 joules for the system. Sometimes in the book you'll see them put a plus sign here. Do you need the plus sign? No, you don't need the plus sign, but it's just kind of emphasize, hey, this is positive number, right? If it was negative, there'd be a negative sign. Any questions? The answer is 71. Okay, what did I do? I did 559 minus 448. Okay, let's fix that. Yeah, so it's written out correctly, but I punched into my calculator wrong. That happens to everyone. There we go, 71. When you get an answer wrong, the first thing you should do is check check the math, check what you did with your calculator. If you did what you wrote out correctly and it's still wrong, then you can go looking for other reasons.